where I put my laptop. I don't. We don't need to move this, but maybe.
Do you have it on a flash? Oh, you want to put it here?
Oh, nice.
That's nice. Thank you.
Perfect. So I take this, or is there a second one? No. I think this.
Okay. You want to do that between your talk and Travis?
Yeah. Well, when he's in the whatever the question, isn't that when we're supposed to do it? To switch it over?
Yeah.
Wait, what do you?
When he's going to be giving the second talk live, and Travis is online, so he was just checking to see if his hardware was going to be okay.
So we can't. Oh,
Yeah,
oh, okay.
because this is the master.
Right. Yeah, I can do that.
Okay.
That's why I just like want to understand how it works. So I don't need this then.
No, you just have to zoom in.
Your flash drive. Well, I mean, I don't know if it's.
Anarada, did you say
Maybe
Travis
I
is
can do
online?
that as a backup. So. I was going to do the Zoom thing, but maybe it's better to do it through here. Because now my talk is finished, I think. Well,
Okay.
find it.
Good morning. This is session 4, quantum simulation and metrology. Our first speaker today is going to be Travis Humble. Travis is Deputy Director of the Department of Energy's Quantum Science Center, a distinguished scientist at Oak Ridge National Laboratory, and Director of the lab's Quantum Computing Institute. Travis is Editor-in-Chief of ACM Transactions on Quantum Computing, Associate Editor for Quantum Information Processing, and Co-Chair of IEEE Quantum Initiative. Travis also holds a joint faculty appointment at the University of Tennessee, Dresden Center for Interdisciplinary Research and Graduate Education to work with students developing energy-efficient computing solutions. Travis received his doctorate in theoretical chemistry from the University of Oregon before joining ORNL in 2005. On a personal note, I first met Travis through a student we had at URI, Ron Sadlier. Ron worked with Travis during the summer between his junior and senior year. And following his senior thesis that he did in conjunction with Travis and myself on superdense computing or superdense coding, he went to University of Tennessee with Travis as his mentor. When we first started planning this conference back in 2019, I contacted Ron, hoping to make contact with people at ORNL and Travis Humble in particularly. And Ron was very helpful in putting us in contact. Unfortunately, in the intervening years, Ron passed away. And so Ron is truly responsible for Travis being here today. And with that, I'll introduce Travis. Welcome.
Oh, thank you so much, Lynn. I very much appreciate the invitation and the opportunity to speak today. As you mentioned, Ron Sadlier, of course, was the common connection that brought us together, and I'm forever grateful to him for this opportunity and, of course, the opportunity to talk with everyone. I apologize for not being able to visit in person. I hope I'll be able to communicate with you some of our interest at Oak Ridge on discovery and innovation with quantum simulation. Let me go ahead and try to get things sharing properly. Okay. So, as was mentioned, at Oak Ridge, we have a quantum science center that is focused on the development and discovery of new quantum technologies. And today I'm going to give you a little bit of insight into how we are approaching this topic of quantum simulation, which I know is the focus of the morning session. Of course, Oak Ridge is a Department of Energy federally funded research and development center. You can see here a panorama of the campus. It consists of many different facilities. Over on the right is the high flux isotope reactor. Up on the left is the Spallation neutron source and Center for Nanophase Material Science. But I wanted to start our story today about what's in the center of all of this, which is our computational and computing sciences complex. This is actually home to some of the nation's fastest high-performance computers, and it actually is a good starting point for this question of what is the impact that quantum computing and especially quantum simulation can have on the nation's discovery and innovation. At Oak Ridge, we have a long history of developing high-performance computers, supercomputers, like the three shown here. These are massively parallel processing systems. They're accelerated by computational devices, in this case, GPUs, that offload and are specialized to solving specific scientific calculations. In the center, we actually have the Summit system that's currently up and operational since 2018. But in a matter of days, we will unveil the new Frontier system. This is expected to be the country's first exaflop system and probably one of the most powerful supercomputers in the world. It is, again, a massively parallel processing design. It uses GPUs attached to CPUs. But there's an enormous question about, well, what comes beyond Frontier? How do we continue this timeline of accelerating computation? And in particular, does quantum computing play a role? Now, here's just a figure of what the facility looks like where Frontier is housed. You can see the racks of computer servers that make up this enormous warehouse-sized data center, the massive amounts of power and water cooling that are required to operate this machine. So it's an incredibly high bar to state that quantum computing or quantum simulation will someday make an impact on these types of facilities. But it's exactly the one that I think we should be thinking about now, because there is many opportunities where the ideas of quantum mechanics and especially quantum computing could make a difference on these types of pictures. When we look at the types of applications that can be used on supercomputers, we find that quantum mechanics is inherent to many of these. This pie chart divvies up the amount of time that's actually spent on the supercomputers at Oak Ridge solving problems of different types. You can see physics, astrophysics, material science, biology, chemistry. I'm sure none of us would be surprised to know that quantum mechanics lies at the heart of these models. Engineering and earth science, of course, may seem more removed, but these also have connections to the quantum mechanical degrees of freedom that describe fundamental processes around the earth, as well as metallurgy and engineering. So given this breakdown of where we think computation actually is taking place and the types of models that are necessary to motivate these types of high-performance computers, it's probably no surprise that the statement made by Richard Feynman nearly 40 years ago is very prescient. If you want to make a simulation of nature, you'd better make it quantum mechanical. And I think this is a great way of introducing the idea that quantum computing, and especially quantum simulation, has a role in our future for scientific discovery and innovation. Again, many of the problems that we are currently facing right now using supercomputers to solve are fundamentally quantum mechanical, and those types of models may be more easily simulated using computers that operate on the principles of quantum mechanics. Now, of course, Feynman went on, and there's a second half to this statement, and I think this is what brings us together today, is because, by golly, it's a wonderful problem because it doesn't look so easy. And it's the other side of this coin, which is that the ability to control the individual quantum mechanics, the precise control of individual atoms and electrons in order to encode information and process that information is a wonderful problem. It's a wonderful scientific problem and a wonderful engineering problem, but it's a problem that has significant consequences. And so I think this is a great motivation for us to pursue these endeavors. Now, in terms of what are the types of systems that we could attempt to use for quantum computing, There are many different types available. Atoms and ions, I think, are one of the most straightforward connections to Feynman's original statement. Here, the individual electrons contained within these atoms can actually be used to encode information, the zeros and ones that form the basis of our information theory. But of course, superconductors, semiconductors, they can also be used for encoding information in the charge states of these devices, either in the superconducting circuits themselves or in donors implanted into the materials, which are then controlled externally by these overlaid electrodes. And then finally, a fourth class of materials for quantum computing that we're interested in at Oak Ridge is based on the idea of exotic quantum states that can exist within materials, and in particular, topological materials. Now, we've yet to actually demonstrate that topological materials can support quantum computing, but there are some great ideas and some great benefits if we were able to. So this is certainly an area that we're pursuing at Oak Ridge. Now, what's remarkable is that in all of these topics, there's been significant advances, especially within atoms and ions and superconductors. We've seen remarkable devices emerge over the last 20 years that actually demonstrate the fundamental principles of quantum computing. And these are just the initial stages of this technology, but it's remarkable that we're able to actually have devices, things that we can poke with a stick, if you will, and test these principles that Feynman originally proposed. I will point out that on the other cases, in the case of semiconductors and topological materials, there's also been remarkable progress. Semiconductors in particular take advantage of our existing computing technology base, and so there's a lot of promise there, whereas topological materials are still in a mode of discovery, and we're still trying to figure out exactly how to control those types of materials to demonstrate these properties. But the point is that we have now some systems that we can actually begin to test and evaluate. And this is one of the things that we focus on at Oak Ridge, is the testing and evaluation of quantum computers. At a very fundamental level, we can begin to look at their basic device metrics. DiVincenzo first proposed some fundamental criterion for how quantum computers must operate. They need to have a scalable system of qubits. They need to be able to be initialized. They need to have gates with high fidelity and duty cycles, which is our way of defining the ratio of coherence time to gate operation. And then, of course, the measurement or readout fidelity. And we can actually quantify these running straightforward tests on these devices. They can be programmed, we can collect the output, and much like physics experiments, we can perform statistics on these in order to quantify these specific device metrics. This is something that I actually enjoy doing at Oak Ridge because it gives me insight into how the technology is progressing, and in particular, where are the areas that appear to be improving the best or appear to have stagnated over time. I think at the moment, we're seeing an enormous amount of progress in the development of these devices. The 4 examples shown here are just points in time. Each of these vendors is continuing to develop and refine these technologies, and you can expect these numbers will change frequently and in fact increase over time. But that change or fluctuation in these device metrics is actually going to be my first stop along this research talk. In the idea of benchmarking the stability of NIST devices, we actually have to address the issue that computational accuracy is quite different from device stability. You can see in the picture on the right something that tries to break up these two ideas. You can of course, have something that is very stable but not accurate, in which you're missing the bullseye, but you're still localized in a particular part of the target. By contrast, at the far right, you can have something that is stable and accurate, in which not only are you clustered together in a tight ring, but you're also focused on where the target or the bullseye is located. When we take these same types of ideas and apply them to the device metrics of today's quantum computers, noisy intermediate scale quantum devices, we can see that there are in fact fluctuations in these device metrics that may undermine the idea of stability. Now, stability is, of course, incredibly important for scientific research because it undermines the idea of reproducibility of results. If I run an experiment on a particular device on a particular day of the week, and another group runs that experiment on a different device on a different day of the week, how likely is it that I'm going to observe the same results from both investigations? And we took the approach of trying to quantify these fluctuations in device metrics, looking at similarity measures, in particular using something called the Hellinger distance, which can be defined on both continuous and discrete distributions. We looked over time across registers, that's the individual qubits in the devices, and then between devices themselves to try to understand how those original DiVincenzo criteria actually fluctuate. And I'll just give you a very short sampling of the results from that. For the case of a 5-qubit device, this is from the vendor IBM called Yorktown. We looked at data accumulated over the course of a year from March 2019 to March 2020. And I've only been able to show 4 of the 5 qubits on this slide due to space, but you can see in the measure of the initialization fidelity, this is basically a quantification of how well we can read out the 0 and 1 states. The red line represents the average of that fidelity, while the blue lines represents the variance of that distribution. And you can see that the fidelity is relatively high, certainly at least on this scale, though there are significant dips that may occur at different points in time. Now, over the course of a whole year, you certainly expect the machines that are operating these devices, the refrigerators, the electronics, the control systems, are frequently being monitored and calibrated. And so these fluctuations are entirely to be understood in terms of the operation of the device itself. But I'd like to call your attention to the lower panel in each of these plots, which actually represents the Hellinger distance, which is the distance between the original distribution located in June 2019, I'm sorry, in March 2019, and the distribution that is observed at each point in time along the x-axis. And you can see that the distributions start to shift, and they don't shift necessarily in one direction, and they don't shift uniformly across the individual register elements. Rather, we start to see what I would consider unstable behavior in the performance of the device. So that is to say that if an experiment performed in June 2019 was performed in June 2020, the likelihood of us getting the same results is very, very low, because the likelihood is that the device itself is very, very different. So this has been an example of looking at the individual time fluctuations across the register elements, but we can also look at how the fidelity, again, the readout fidelity, varies between register elements within a single device. For this, we looked at the 27-qubit IBM Toronto device. We picked a particular day, 11 December of 2020, from the window of 8 o'clock to 8:30 a.m. UTC. And here we've actually measured the correlations between the individual readout fidelities, the distributions of those, and then looked at how those distributions vary between qubit registers. Let me just give you an example. Up here in the inset, you can see that qubit 11, its readout fidelity actually has a distribution that looks like this orange hill across the x-axis, whereas qubit 0 has a much steeper fidelity located around 1. Now, of course, qubit 0 here is the better qubit, but the question is, how do the distributions themselves change across all the qubits in this device? And these areas where there's dark red bands, this is qubit 11 in particular, actually has very poor similarity with any other qubit in the device. And again, it's the worst qubit, so that's not necessarily a surprise. But you can see that there are other qubits, for example, down here in the region of 4 to 8 and 18 to 24, that give a nice blue field. And this corresponds to a small Hellinger distance, which therefore indicates good similarity. So again, the point here is that in benchmarking this devices, the computers that we have available today, there's many different metrics that we need to monitor, including the DiVincenzo criteria and their fluctuations. But of course, those are not the only metrics that are important. One of the things that is most important is what are the actual applications that we can run on these devices, and in particular, applications of quantum simulation. So we know already that by Feynman's original statement that we expect nature itself will be a good model to try and simulate on quantum computers. Whether we're looking at topological quantum materials like the quantum spin liquid shown up here in the top left, or the fundamental interactions between high energy particles like the scatter shown here on the right, quantum mechanics have a straightforward mapping into those models and therefore a straightforward understanding of how they may be executed on these quantum computing devices. What may be less obvious at first is that there are other problems, such as routing and transmission, logistics, or combinatorial optimization, portfolio modeling, that actually can be reduced down to formulations that are expressible using quantum mechanical models, and more importantly, are more easily solved within those quantum mechanical models. So the applications of quantum simulation extend far beyond Feynman's original statement of simulating nature, but actually get into simulating many of the different scenarios that we face within our country in terms of solving hard computational problems. Now, what underlies all this, of course, are the algorithms. We already know that there are quite a few algorithms available for demonstrating speed ups, that is, fewer steps to solve these problems. Quantum simulation is one, calculating partition functions or performing discrete optimization. Factoring, of course, was one of the leading examples that engaged a lot of people early on in quantum computing. But what's most interesting, I think, for me at Oak Ridge is that I can map these algorithms onto those domain-specific problems in high energy physics and material science or chemistry that actually lead to a practical advantage for the demonstration of quantum computing. And so I'd like to talk about that in the context of quantum simulation, and in particular focusing on this idea of doing quantum simulation in the physical sciences. And that could include chemistry, materials, high energy physics, biological systems. This example, in fact, is for the case of chemistry with some connections back to biological and earth sciences. This actually represents a cartoon diagram of nitrogenase, an enzyme that exists within bacteria that inhabit the soil. They're responsible for the creation of ammonia that is necessary for the development of plant life. And you can see up here this idea of taking nitrogen and hydrogen from the air and creating ammonia, is actually facilitated by this enzyme that's located in the center of this, known as FOMOCO. It's a heavy metal complex whose electronic transition or transfer reaction is actually responsible for enabling this type of chemical reaction. Now, it's an incredibly interesting reaction because it may be useful for solving some of the most challenging problems in food security, which include the creation of fertilizer. And so if we were able to understand better how these heavy metals were able to address this type of chemical reaction, then we might actually get some insights into how we could improve our own food security and production of fertilizer. Now, the problem, though, is that these heavy metals are actually many electron problems. Correlations within the electron's behavior play an important role in understanding this chemical reaction. And it's not so straightforward to model, even with our supercomputers for today. Quantum computers may be able to provide an advantage here if we can map those quantum mechanical models onto quantum computing devices. Unfortunately, when you do some back of the envelope calculations on this type of model, you quickly realize that the few qubits that we have available in today's devices are insufficient for performing these types of calculations. By all estimates, we're probably looking at on the order of 1 million, if not 10 million, physical qubits necessary in order to perform calculations of this caliber. Well, that may not seem very encouraging given the current state of the devices, but the truth is there's a lot of space in between this holy grail problem and what's available to do on today's devices that, again, enforce our discovery and innovation with quantum simulation. In particular, on today's NISQ devices, we can actually create algorithms that work in these small qubit regimes and test out the principles of quantum computing. In particular, there's an algorithm known as the variation quantum eigensolver that's based on the variational principle, and it searches for a quantum state that can minimize the energy defined by a Hamiltonian. You see here the Hamiltonian H defined on the right. This objective function, which is of course the expectation value, is then minimized with respect to a parameter theta that parameterizes the wave function psi. Now, the kth iteration of the wave function psi can be decomposed in terms of these unitary operations, where each of those are again parameterized by this kth value. And of course, that may be done iteratively so that it depends on successive applications of the operators or in a straightforward way. So just to put this diagrammatically, if I could prepare a register of, let's say in this case, 4 qubits, and I apply my state preparation operator, my sequence of unitaries for a given choice of the parameter theta, I can then estimate the energy through the Hamiltonian, performing that measurement in order to get a value for what I think the minimum energy is. If I've met that threshold for my optimization problem, I would consider myself done and then output that minimization or the energy at that particular value of the theta parameter. However, if I've not yet reached convergence, I would then cycle back, update my parameter theta, and perform a new execution on my quantum computer in order to estimate the revised energy. By performing that loop in sequence, I can actually converge to what I hope is the correct solution for this problem. Now, that, of course, is a little bit abstract. We can model this in the terms of chemistry by taking advantage of the fact that the chemical models for the electrons and nucleus that interact in a molecule actually can be decomposed into the operators necessary for just implementation on a quantum computer. So in particular, taking this molecular Hamiltonian, making the Born-Oppenheimer approximation, and then performing second quantization, I can decompose this down into a sum of electronic fermionic operators that are actually describing the excitations of the electrons within the molecule. From here, I can derive the electronic ground state and therefore use the variational quantum eigensolver to get an estimate of what that ground state energy is. Similarly, when I construct the ansatz or the circuit that describes that wave function, I can use existing chemical theory, in particular unitary coupled cluster theory, to derive what would be the best circuits to use in this parametric approach to optimization. With the unitary coupled cluster theory, I can actually expand out what the excitations operators are and truncate them at different orders. Singles and doubles is very popular, especially for the types of ground state molecules that we're going to be thinking about. Here, the approximation then is decomposed from the fermionic operator into a spin transformation. These types of transformations, such as Jordan-Wigner, actually now translate the ladder operators, A's and A's daggers, down into Pauli operators, the X, Y's, and Z's that characterize quantum computing theory. Here, the singles and doubles operators can actually be decomposed down into individual pairs of Paulis or quadruples that are then implemented on the quantum computer. Now, the execution of those types of circuits can then be used to estimate what is the minimum energy for these molecules given those ansatz wave functions. And this leads to the rise that quantum chemistry can actually be used as a benchmark for these types of NIST devices. Yes, of course, it depends on the accuracy of the theory as well as the decomposition techniques that we're using. But the ability for the quantum computer to actually estimate the energy within the bounds of those theories gives us an insight into its practical use. Here on the left, what you're seeing are estimates of the energy for sodium hydride using the frozen core approximation and the 4-qubit wave function that we were talking about earlier. The red, the solid black lines represent the analytical results. So this is what we would expect given these ansatz wave functions and these Hamiltonians. The red lines or the red triangles actually represent the data that comes back from the quantum computer. And I would claim, for the top is for the IBM device and for the bottom is for Rigetti. Both of these are superconducting qubit devices. I would claim that the red line or the red triangles actually don't match very well the black analytical theory. And of course, that is due to the noise in the system. But we can remove some of that through classical post-processing and actually get a fairly accurate representation of what the original ground state would be. And this makes a huge difference between the raw data and the quote unquote purified data when it comes to evaluating the status of the device itself. The closer that the raw data gets to the purified data, the less quantum error mitigation is needed in order to collect this result. And that itself becomes a quality factor for evaluating these devices. Now, of course, this may vary with the device. It may vary with the type of molecule. It may vary with the type of ansatz. And so the table that you see over here is really just a way of indicating that there are many options available for benchmarking these devices. And any individual point experiment itself is probably not very informative on the behavior or the quality of the device itself. But rather it's the fact by looking over a suite of different benchmarks and evaluating how each of those behaves that we start to get some insights into what is the actual practical utility of these quantum computers today. And I think we're seeing a lot of progress right now in the area of quantum chemistry as a form of quantum simulation that indicates that we're at least headed in the right direction. But there continues to be these air gaps between what the raw and the purified data looks like. Now, of course, all of this is rather sophisticated and becomes quickly complex when you imagine trying to translate these Hamiltonian expressions, these quantum circuit expressions onto actual hardware. And so at Oak Ridge, we spent a lot of time developing software tools that enable programming quantum computers, including for chemistry. And I'll just briefly mention the two main repositories here, the XACC middleware, which is responsible for a hardware agnostic way of connecting to many different types of devices, including IBM, Rigetti, D-Wave, Honeywell, and others. And then QCore, which is a high-level programming language that, again, is hardware agnostic, but available in both C and Pythonic forms. Please feel free to check out the websites for more on that. I wanted to move on to a second example of how quantum computers can be used for simulation, in this case, material simulation. There are, in fact, some very interesting questions about how spin systems behave in the presence of frustration. And this gives rise to many complex behaviors. One of these actually is the case of holmium tetraboride. On the right, you can see that as a magnetic field is applied to this particular type of material, the magnetization of the material goes through different plateaus. Of course, at a very high magnetic field, it saturates almost to 1, but in between, there are these fractional magnetization plateaus that indicate some complicated spin dynamics within the material whose lattice is shown on the left. The question is, can we use quantum computers to try and simulate that type of problem? And there is a toy model called the Shetterly-Sutherland icing lattice that is believed to describe fractionalization in these magnetization curves. This is based on the types of icing interactions that you see in the diagram on the left. The blue square lattice is described by the J1 ZZ terms, and then the dashed red lines are described by a second coupling constant J2, but again given as ZZ. So this is a classical icing model that's not fundamentally quantum mechanical, but it does give rise to these complicated frustrated systems that are generally difficult to calculate. And that frustration produces a phase diagram like the one you see on the right. There are at least 4 different phases: the ferromagnetic phase, the dimer phase, the Neal phase, and this 1/3 plateau, or the fractional magnetization phase. And the question is, can we use a quantum computer to simulate this particular phase diagram? And the answer up front is yes, we can. And these are actually the results that come from using the quantum computer to simulate that phase diagram, where the highlighted heat map actually indicates the magnetization. Now, how that actually is done is by using the D-Wave quantum annealing processor, which is a variant of quantum computing in which the prepared qubits, in this case, are flux qubits based on superconducting, and they're networked together in the lattice that you see on the right, what's also known as the chimera lattice. By initializing the state of this processor into a well-known initial state, uniform superposition, and then annealing or adjusting the quantum dynamics of this system slowly enough, we can actually drive the population from a uniform distribution down to the configuration which corresponds to the original Shetterly-Sutherland icing Hamiltonian we were just talking about. There's a lot of details that go into how to embed that particular type of problem into this lattice, but I'll skip over them for the sake of time and instead emphasize that it is the control of the annealing time, or the dynamics themselves, that enable us to accurately prepare the minimum energy configuration of this particular lattice. And what we find when we run that program and perform measurement is that we actually get a rather good representation of what the different phases look like. On the left is the phase diagram we were talking about earlier, whereas on the right is an actual 512 spin lattice describing the orientation of the individual spins that were measured. So here we'll call red squares spin up and black squares spin down. And in the ferromagnetic phase, we actually expected everything to be pointed in the same direction. And then the simulation gives a rather relatively good approximation to this. You can notice that things along the boundary conditions actually have some errors in their configuration. But again, near the boundary, it becomes more difficult to control the spin dynamics. When we go into the anneal phase, we actually observe this checkerboard pattern that characterizes those particular dynamics. Again, a rather good representation of what should be expected. I'm sorry, this was the dimer phase. Oh no, I'm sorry, that is the anneal phase. Whereas then when we go into the fractional magnetization phase, what you actually notice is this curious threesomes of the spin would actually give rise to that fractional factor of 1/3 magnetization. And what's remarkable for me is that all of this was done using the quantum computer. So for each of these individual phase diagram areas, we run the experiment many times in order to collect an ensemble of these types of spin configuration. And it's from that ensemble we can actually make more interesting calculations, including the static structure factor that characterizes the material itself. And so in this animation, what you're seeing on the left is the longitudinal field HC is being slowly increased, and the magnetization of the material is going through its fractional magnetization plateau, so around the value of 1/3. Now, of course, this doesn't quite perfectly match the holmium tetraboride example, which had multiple plateaus, but at least captures the fundamental behavior that we were looking for. Now, I will point out that all of this has been compared to classical quantum Monte Carlo calculations. So we have some sense of where the quantum computer deviates from the conventional approach. But what is even more interesting to me is that we can actually use the data from the quantum computer in a second calculation. In this case, it's Fourier transform over space in order to compute the static structure factor. This is basically the amplitude located in momentum space. And this is something that is directly measurable from neutron scattering experiments. So you can take these materials such as holmium tetraboride, put them into the neutron instruments that are located at Oak Ridge, recover the static structure factor, and now make a comparison with the quantum computing calculations. And so this is exactly what we've done at Oak Ridge. And you can see that this particular simulated structure factor gives rather good agreement with the 4 lobes that we expect to see in these intermediate fractional plateaus. Now, the reason we've been able to do all this is because we have access to these quantum computing devices. At Oak Ridge, through the Leadership Computing Facility, the same place where we are installing the Frontier system today, we have a quantum computing user program that provides access to quantum computing resources for the purposes of understanding how to integrate quantum computers, well, into conventional computing, but also into scientific workflows. So whether it's chemistry or material science or high energy physics, understanding how these devices can be used, even in these early days, becomes incredibly important to anticipating how they may be used in the future. Now, the quantum computing user program itself has several priorities. The first is to enable research, and that is largely to provide access to users so that they can begin testing ideas out on these types of systems. And then, of course, evaluating the technology. Like we were talking earlier for the stability evaluations, we want to get an insight into how well the systems behave, not just at points in time, but also how they're are predicted to behave over the course of the near future. And then finally, to engage the community. And here you can see a collection of the many people that we have working at Oak Ridge. And there in the center, of course, is Ron Sadlier from the University of Rhode Island, who played an important role in our understanding of how quantum computers themselves actually are able to operate today. And then, of course, how we can develop software tools to enable their future growth. Now, just to give you 2 highlights from the program itself that actually come from other people. The first, out of the Lawrence Berkeley National Laboratory, was using the IBM system to, again, do quantum chemistry calculations, but this time they added a rudimentary version of error detection. So by encoding information into a subspace of a collection of qubits, you can actually use measurement to reduce noise. And here, their version of VQE actually found that a 6-qubit example with this error detection mechanism gives improvements over the straightforward 2-qubit approach. And so that's I think an important example of how the user program itself has helped enabled new science in this area of quantum simulation. And then from a team at Oak Ridge, they actually were the first that I know of to use 2 different quantum computing systems to perform simulations and then combine the results together. And then in this case, they were doing the calculation of the nuclear binding energy of deuteron. This is basically heavy hydrogen without the electrons. Here they run their VQE calculation partly on an IBM system and then partly on a Rigetti system. And you can see these curves corresponding to those parameter optimizations of the individual components, the individual polyterms that make up the estimate. And again, what I find remarkable here is that they were able to actually run on 2 different quantum computing systems and combine the results together. And that gives us some hope that there is a way of transferring results across systems and actually using them in scientific computing. Now, engaging the community, we have annually a quantum computing user forum. Of course, I invite everyone here to attend. The next event is likely to be in April of 2022. This is a place to showcase all the work that's going on in quantum computing, including quantum simulation. As normally located at Oak Ridge National Laboratory, I have my fingers crossed that we'll be able to do that this year. And then, of course, online access will be available as well. Now, all of the work that I've talked about has been on a more modest scale than what we've just set out doing in the past year. And the Quantum Science Center at Oak Ridge is one of the 5 National Quantum Information Science Research Centers. It is a 5-year effort. It's $25 million per year. It's over 100 people coming together to realize the potential of quantum information science for American scientific leadership and national security. And we have 3 goals that we focus on. Accelerating quantum information processing. This gets into the development of the topological qubits we were mentioning earlier. Predicting new physical and chemical behaviors. This resonates directly with the ideas of quantum simulation that we're talking about. And then enabling exploration of the previously unmeasurable. And this is using the ideas of quantum sensing to enable new types of sensings and measurements. Now, as I mentioned, it's a collection of 16 different institutions. It's led by Oak Ridge, but there's many others involved. 3 national laboratories and 9 universities and 3 companies. So it keeps us busy with over 100 scientists and engineers, a few of whom I think are actually speaking at this conference. We actually have a rather broad research portfolio. And what has become the interesting bit is how we tie those pieces together. So our goal is to overcome these roadblocks that we anticipate are going to prevent the scaling up of quantum technology. The NISQ devices of today are great playgrounds for discovery and innovation, but the long-term application is going to require some innovation. In particular, I'll draw your attention to the center row, quantum simulations for scientific applications. We are focused on translating these ideas that we've been talking about into predicting new physical and chemical behaviors, whether that's materials or chemistry or high energy physics. And the way we're doing that is by developing these new types of simulation platforms, quantum simulation platforms, and tailoring them to scientific applications. In our materials research thrust, we are focused on the development of new types of materials, including new types of quantum spin liquids and topological electronic materials. We're taking advantage of things like the spallation neutron source that I mentioned earlier to recover evidence that we can actually prepare these Majorana modes in some of these materials, as well as these entangled ground states like in the quantum spin liquid. And for those people who don't know, on the right is an example of quantum spin liquid, ruthenium chloride. I must admit, I was quite surprised to realize it was not a liquid, but in fact a crystal. And the liquid refers instead to the behavior of the electronic structure within that molecule. So we are pursuing this types of discovery in order to build new types of qubits that may eventually be based on these types of topological properties. In our computational science, we're focused on quantum spin liquids and other types of exotic quantum systems as demonstration problems for how we can use both conventional supercomputers as well as exotic new quantum computers for solving their chemical and physical properties. And in this case, we have a variety of different technologies within the Quantum Science Center, including ion traps and neutral atoms, superconducting qubits. that we're using in order to try to solve these types of problems. As I've outlined here, though, it is a very difficult way to piece together many different types of concerns, including the hardware, the software, and the application. And so combining together all of these different research topics is part of what the center focuses on. And then finally, in the area of sensor science, we have a remarkable collection of different techniques that can be used in order to build hybrid quantum sensors that actually look at the properties of exotic quantum materials, as well as those that look at the properties of what we have yet to discover, including dark matter. So we have a number of different efforts focused on these different areas. In particular, I will note that we are planning a new type of characterization field facility at our partner Fermilab, which is buried underground and intended to be used for characterization of quantum materials in the absence of cosmic radiation. So we've referred to this as the quiet facility. And in particular, we hope that that'll be able to help us get better understanding of the types of dynamics that we observe in all of these exotic systems. Now, within the realm of the quantum simulation for scientific applications, we've only been around for 1 year, but we've already had a remarkable series of demonstrations that hint that we're headed towards something useful. In our areas of ion trap development, we've begun developing one of the initial cryo-cooled ion traps, relatively small demonstration scale, but it's intended to be used for analog quantum simulation methods. And that's driven by our advances in cryoelectronics from our partners at Fermilab, who are actually able to create digital waveform generation techniques that can exist inside of these cryogenic refrigerators. Similarly, at Pacific Northwest, they've developed HPC simulations that can extend up to the large scales necessary to test when we can demonstrate quantum computers on problems of significance. And then finally, our collaborators at Los Alamos are looking at new types of algorithms, including those tailored to applications, such as the dynamics of neutrino clouds that are observed inside of dense matter. Now, all of these individual efforts, of course, are combined together through the center to bring this integration to bear, to demonstrate that we can actually reach useful quantum simulation applications by having a multitude of efforts and a multitude of pathways. This is only a few snippets of examples of how we're doing that, but the overarching picture is that we're focused on this idea that we can translate fundamental quantum simulations into practical applications. On the left, you'll see this swirly diagram indicating the complicated dynamics of individual particle physics, such as neutrinos, which of course underlie the behavior of many objects in our solar system, including the sun. In the middle, understanding the superconductivity, in particular high temperature superconductivity, would have a significant impact on our ability to transfer energy, including through low voltage but high current transformers like the one you see at the bottom. And then finally, understanding how catalysts such as iron actually can be used to improve processes such as ammonium creation that we were talking about earlier, will give rise to new techniques to enable clean and green energies, such as Knoxville that you see down there in the lower right. My point of ending with this slide is not to say that we can do these types of calculations today, but rather to say that this is exactly the type of discovery and innovation that quantum simulation will enable in the future. By pursuing these types of research and development, we can in fact address the problems that are raised by those figures shown in the top row in order to enable the solutions that are shown by those in the bottom. We may be many orders of magnitude away from being ready for those types of efforts, but the truth is that we are headed in that direction. So in summary, from my point of view, quantum simulation is offering many new opportunities to accelerate discovery and innovation in science. It is early days though, and we are still assessing the impact of these ideas and learning the best practices. But these high value opportunities of the future will require significant advances. We know that, especially at scale and in terms of resilience. But we look forward to this problem, and as Feynman himself said, by golly, it looks wonderful. So thank you very much.
Thank you, Travis. Thank you, Travis. We do have one online question.
Yes, we had one online question. Engaging the ecosystem, when compared to classical computers, what is the environmental impact of quantum computers? How will quantum science impact our natural ecosystems locally, globally? That is, server farms being built in cold weather climates.
Oh, that's a wonderful question. I very much agree that there is a footprint that we expect for quantum technology, and that footprint will have an impact on our environment. There are some arguments that the quantum technology itself may end up being more energy efficient. You know, controlling individual electrons takes less energy than controlling many electrons. At the same time, this technology, though, is still very early in its development, and so I'd hate to commit to any particular types of efficiency arguments yet. Of course, there is also the possibility that quantum approaches may give us new insights into how we should solve problems in energy and energy security. You know, as Lynn mentioned in the beginning, when Ron and I were working on the case of superdense coding, you know, one of the remarkable examples there is that you can actually transmit more information using less energy. Again, it's very early in the development of those ideas, but this just hints at what quantum computing could offer in this landscape.
Hi, Travis, this is Kathy McGew. I actually have a question about your the first part of your talk with the you know, the benchmarking of the components of the gate model computation, and I guess I wasn't clear on whether these, you know, the problems you see, are they going to go away when error correction is in place, or do they have to be fixed before error correction can be applied? What's the prognosis, I guess? What are the prospects for fixing those problems?
Oh yeah. Hey, Kathy, I appreciate that question. So I do think that these fluctuations in device metrics that we are observing is more of a operational concern. You know, that may mean that more frequent calibration, or at least some attention to how calibration is performed, needs to be included in the operating of these devices. I do not think that most devices at the moment operate with set tolerances, or at least that doesn't appear to be the case. But by adding things like tolerances, you know, what is considered acceptable fluctuations, I think that may be the way to address this. In terms of addressing or what the consequences may be for things such as error correction, I do think if the device noise model is fluctuating in time and space, then it's going to be very difficult to have assurances that a given error correction code is actually operating at a specified level. So these tolerances ideas may eventually play into that.
Thank you very much, Travis. Thank you, Travis. Let's give him a hand. Very nice.
Wonderful. Thank you very much.
Hello? Okay. Our next speaker is Jeremy Levy. Jeremy is Distinguished Professor of Condensed Matter Physics at the University of Pittsburgh and founding director of the Pittsburgh Quantum Institute. He received his AB degree in physics from Harvard in 1988 and a PhD degree in physics from UC Santa Barbara in 1993. After a postdoctoral position at UC Santa Barbara, he joined the University of Pittsburgh in 1996. His research interests center around the emerging field of oxide nanoelectronics, experimental and theoretical realizations for quantum computation, semiconductor and oxide spintronics, quantum transport and nanoscale optics, and dynamical phenomena of oxide materials and films. He is a class of 2015 Vannevar Bush faculty fellow, a fellow of the APS and the AAAS, a recipient of the 2008 Nano 50 Innovator Award and the NSF Career Award. He has received the University of Pittsburgh's Chancellor's Distinguished Awards for both research in 2004 and 2011 and for teaching. And very pleased to welcome Jeremy. Oh, one other thing. He was also Vanita's dissertation advisor. Jeremy.
Thank you. Can people hear me? Is this, are these lights on? Okay, great. Well, I'm really delighted to be here. And yes, so I think that would have been the best introduction, just to say that I was Vinita's advisor. But I'm really, really thrilled to be witnessing the launch of this quantum program and the launch of Anita's independent academic career here at the University of Rhode Island. I want to talk a little bit about my own research interests, especially as it intersects with the theme of this session, which is quantum simulation, but maybe taking a step back and thinking about how different components of quantum materials and quantum information fit together. So let's see. But yeah, I do want to mention that I'm also the director of the Pittsburgh Quantum Institute, which has been in existence since 2012. And we have a mission of unifying and promoting quantum science and engineering in Pittsburgh. We have more than 100 faculty members from the University of Pittsburgh, from Carnegie Mellon University and Duquesne University. I also want to advertise that we now have 6 open faculty positions this year in areas of quantum science and engineering, 3 at Pitt and 3 at Carnegie Mellon. So we're really gearing up to to address the most challenging problems from the vantage point of many different disciplines in Pittsburgh. I also want to point out, and again, this is a thematic advertisement that I'm a co-organizer along with Sue Coppersmith, who gave a talk yesterday, of the Aspen 2022 Winter Conference on Quantum Simulation with Quantum Hardware. So I encourage any of you who are interested and also like to ski. Even if you don't, you can sip hot chocolate in the evenings by the fireplace. This is one of these wonderful venue for physics in 4D, right? Which just like what those of us in this room are doing, talking to each other and interacting. This is a really rich environment. So I encourage those of you who are interested in this topic to apply to the program. Well, quantum computing has arrived, I think. We know that. We have clip art. We're working on the emojis, as far as I know. That's going to be another important milestone. Actually, you can go back and in Google, of course, so you can follow trends and understand how the interest has varied over time, although it only goes back to 2004. But if you type in quantum computer, you see these spikes, and I found them really interesting. So there was a spike in 2006, where apparently first commercial quantum computer solved the Sudoku puzzle. There was another one, which I thought was really interesting. The way you could clearly tell the reporter was struggling with what the scientist or engineering was trying to tell them about what they had done. It was both. This is called quantum speed up, right? It was both faster and not faster at the same time. But they were trying to explain, how quantum computers are only speeding up certain types of problems. And then, of course, a really big one, 2019, the Google breakthrough. Of course, we're at the beginning of the second quantum revolution. If you were to compare the keyword of the second quantum revolution, quantum computer, with the keyword of the first quantum revolution, quantum, of course, that's the red curve, right? That's quantum, right? So we have a long way to go before they start overlapping. But it's actually, you probably noticed there's a pattern. I did too when I did this search. And so I decided to do a quantum Fourier transform, right? Which is to do a Fourier transform of the popularity of this word over time. And it's interesting that it has very clear structure and harmonics. And in fact, if you then do a quantum inverse quantum Fourier transform, you'll see the how quantum we are as a function of the time of the year. And I applaud Vanita for we're picking the most quantum time of the year to hold this conference, which apparently is in October. So I don't know, I think NIST people need to understand, the origin of these quantum fluctuations. So, okay, so I'm not going to give a big overview of the whole field. I think there have been wonderful introductions to this area. I want to focus on three key concepts, which sort of guide points for me. Of course, we have the quantum computer, right, which is this mythical machine that is going to speed up lots of types of calculations. And then, of course, it's made up of quantum bits. And then quantum materials are sort of the basis of all quantum bits. And they're also things that quantum computers can simulate. And so there are all these interesting connections between these three types of interrelated concepts. And of course, they're all related by the most important equation in quantum, the Schrodinger equation. So if we think about like where we are right now, and again, I'm not going to provide a sort of full assessment, but if we think of this as like 2021, a quantum odyssey, a nod to Arthur C. Clarke, you could say that we have not quite touched the monolith, right? And so how would I define that? Lots of people can, could talk about quantum supremacy or advantage. I'm going to think of this as being simulating the simplest possible Hamiltonian with the simplest possible quantum computer, right? And the simplest Hamiltonian is h equals 0. So imagine that you have h equals 0. So that means if you plug this into the Schrodinger equation, you know that if you begin in a superposition of 0 and 1, you're going to remain in that state for all time. So this is the simplest possible quantum computer because there's only, it's the smallest one. It's the simplest quantum memory, and it's the simplest quantum material, right? Hamiltonian couldn't be simpler than 0. And yet, no technology can do this yet, as far as I know. Maybe we're waiting for the next news cycle, but I don't think we have that ability to stop time and preserve a quantum state indefinitely. So I would like to go to that museum, right, where they have the qubit that's in the 0 + 1 state with a sign that says, please don't tap on the glass and so forth. I would really like to be alive to witness that point. So I want to talk a little bit about my quantum mindset, sort of which is sort of a lens for how I approach science and engineering in this domain. And to do that, I have to sort of give my quantum origin story. I'm not going to talk about my pre-quantum days, but I joined the University of Pittsburgh in 1996. I taught a few quantum classes. And then there was this pivotal moment for me, which was a lecture that was given by Peter Shor. It was the Dixon Prize lecture that he gave in 1999. And I think this is a picture of him later on, later in life. But the point is that for me, it was really important because he talked about some work at the very end of his talk. It's like, oh, there's this person in Australia, Bruce Caney's work. As I looked up that paper, and of course, I was like, I had my mission. I said, I'm going to enter this field. Of course, it was multiplied by a funding opportunity, but basically a year later, I had a proposal. I gave a talk at my first talk in the subject at the MRS fall meeting, very polite but confused audience. I was telling them about quantum information processing, and this was really not something that was on the tip of people's tongues. But the funding opportunity came from DARPA. There was a program of quantum information science and technology. And I had a proposal that was based on some of the material systems that I was working on, these oxides, combining them with silicon, germanium. So we were off and running. So I was, of course, very interested in this connection with materials because it was sort of this big unifying concept, right? That you could identify these two-level systems in such disparate physical systems. For me, this was a great unifier, an intellectual unification that for me was very important. So I'm not by training a material scientist, but I work with a lot of people who do, and I'm interested in the physics of materials. And so it's really just fascinating to me that you could have such different systems that all are sort of doing the same thing. And you can define two-level systems within such a rich variety of physical materials. So for me, this is sort of a lens, a way of thinking about the world and research and opportunities. So when I am presented with, let's say at a conference or somewhere, of some quantum material, I ask myself, oh, is it a qubit? Like, is there a two-level system? If so, well, that's great. But maybe if not, maybe it can help, right? Maybe it has some property that could be useful in controlling or processing quantum information, or maybe it could be used for quantum simulation. Or maybe it's just a new state of quantum matter, right? Something that's just simply really interesting. If not, then okay, maybe I'm less interested in that system. So in 2006, I was presented with a new quantum material. It was actually through physical travel that I was talking with a group that was that had made this really interesting discovery. These are two insulating materials where the interface between them could be either insulating or conducting, depending sensitively on how many unit cells of this very thin top layer of lanthanum aluminate. So the insulator plus insulator gives you a conductor, but even more than that. So it turns out that if you have 4 unit cells or more, then the interface was always conducting. If you had less than 3 unit cells, it was always insulating. And at 3 unit cells, you could actually switch it back and forth between insulating and conducting states. So it was like a switch. You apply a voltage in the back of this crystal, and you apply 100 volts, and it would switch to a conductive state. You turn off the voltage, it stays in that state until you apply a negative 100 volts. So for me, from my point of view, this was really interesting, but way too big, right, to be, quantum or anything like that. But I had this idea, which was sort of, again, going back to my childhood. I don't know how many of you have an Etch-a-Sketch stored away in a drawer somewhere, but basically it was, stored in my mind, the idea of maybe controlling things locally. And so I was inspired by the Etch-a-Sketch. I didn't draw this. I'm not good at drawing the Etch-a-Sketch, I just like the idea. But if you look inside, basically there's a stylus that is pressed against a plastic sheet, and there's aluminum powder that sticks to that plastic, and you can scrape it off. And when you scrape it off, it looks dark because the light passes through. And it's reversible, so you can turn it upside down and shake it. So of course, that's a toy. We're adults now. We have tools. This is an atomic force microscope, and we have these sharp little tips that can be used to do something very similar to this. So what we do is we take those structures. This is the lanthanum aluminate strontium titanate, and we make electrical contact because, again, these are both insulators. We have to burrow through the lanthanum aluminate, and then we take this AFM tip and we move it across. We apply a voltage to the tip, positive voltage. And what this ends up doing is it leaves a trail of hydrogen protons. Wherever the tip goes, those protons stay. They come from water. And what they end up doing is attracting electrons to the interface. And so you can sketch conductive paths underneath this insulating layer. And you can also erase them. So you just change the sign of the voltage and you can remove those protons. But this is not a toy, right? Basically Etch-a-Sketch is like millimeter scale control. Here we're talking about nanometer scale, extreme nanoscale control of this metal insulator transition. We demonstrated the ability to write and erase features with just 2 nanometer precision. And you can do this over and over again. It's like electronic paper. So really, we were very inspired at the time to think, what are all the things that we can do with this system now that we have the ability to control these electronic properties on extremely small scales, and not just electronic, not just conducting and insulating, but it turns out that sort of major properties of solid state physics are all controllable, like superconducting, magnetic properties, ferroelectric properties, nonlinear optical properties. And so we were really inspired. This was a drawing, was not an Etch-a-Sketch, but you could see even there was a quantum device kind of envisioned, way back in 2009. This was way before we had the ability to do any low temperature experiments. This was sort of a more than decade-long journey to explore and ask the question, what is this system capable of? And so really we want to ask these questions, right? And it's not something that you can just answer right away. You have to go and do research. So we didn't want to get locked into any one particular application because we could be missing the most important one. So we want to open new dimensions. And so we started off, of course, with things that we could do, like making nanoscale transistors and diodes and photodetectors. The whole bottom row here is all the optics that I used to focus on before I started doing quantum stuff. And then we started to acquire low temperature hardware, integrate with other materials like graphene, and make sort of prototype devices like single electron transistors and so forth. And then we really started to look at millikelvin temperatures, looking at superconductivity and taking it apart and trying to understand why these materials become superconductors, and also creating things like electron waveguides. I'm going to talk about a few of these in more detail. So we sort of realized that this is not just a series of sort of disconnected research projects, but really they sort of fit within a paradigm, a research field, which we call correlated nanoelectronics. And so this is a very small field, but it exists at the intersection between two very distinct mature fields. So on the one hand, you have semiconductor nanoelectronics. This is basically, the science sidecar of your iPhone, basically shrinking semiconductor devices to the very small extent, and then understanding. Of course, this is where the spin-based quantum computing has arisen from making single quantum dots, quantum point contacts, and so forth. On the other side is a completely different field, completely different culture, different research groups where they're looking at this rich properties of materials, right? And like Oak Ridge National Lab, of course, was plays a prominent role with these sort of rich physics of materials like correlated oxides, high temperature superconductors, and so forth. But generally not systems that are controlled at the nanoscale. So we want to combine these, but we want to do it in interesting ways. So we really want to have the interesting intersections. And the way that we start, also, we realize that you want to start perturbatively. You want to kind of tiptoe from one field towards the other one. And so this is a type of intellectual perturbation theory. So for example, you could say, well, I'm mostly going to think about some device here. And what happens if I were to add a little bit of the physics from the other material system by swapping out the semiconductor material with the complex oxide? What happens? So this is a bit of a tiptoe, but you can also go in the opposite direction and say, hey, I don't know why this thing floats, right? This is a high temperature. No, people don't know why it floats, right? I mean, they don't know what the mechanism is of high temperature superconductivity, or even the superconductivity in the material that we're looking at, which is sort of a precursor of high temperature superconductors. So the idea of taking a extremely small device that can probe the inner workings gives you insight that you can't get from ordinary techniques. And then, of course, this is a boring rectangle, but it's meant to be like the unknown. Like when you're really in the non-perturbative regime, what are you going to discover from really venturing out into this? So I'm actually going to give very quickly a couple of examples. I will even show you an example of the rectangle. So let me just begin with a brief point that we actually accidentally discovered something pretty important about the superconducting nature by creating a mesoscopic device out of this material. And so I'm not going to talk too much about it, but basically we discovered a phenomenon electron pairing, which is how superconductors are formed, basically from Cooper pairs. But normally they don't like to pair up alone. So they only do it when there's sort of a mean field of pairs around them. But it turns out that with the pairing strength is really strong, you can have isolated pairs. And we discovered this by making a single electron transistor like the sketch that you see here. So the idea was that when we were counting how many electrons were jumping onto an island, we found that they were going 2 at a time and not 1 at a time. And that was wrong. It took us quite a while to discover this, but basically we realized that it's actually a state, a different state of matter. So this would be the superconducting state where you have these coordinated Cooper pairs, and then you have the normal state, right, of these individual electrons doing their own thing. So the idea was that you have pairing without the phase coherence. And this is a phase that we discovered in this material system that was predicted 50 years before. So I want to give another example of how when you make a device in a sort of paradigm of, let's say, mesoscopic physics, and you replace the material, sometimes really strange things can happen, or very interesting things. And so I want to talk about quantized ballistic transport of electrons and electron pairs and electron waveguides. That's a long title. But an electron waveguide is really sort of what it sounds like. It's kind of like an optical waveguide or optical fiber where you have modes, but these are fermions, not bosons. And so these electrons, though, they have a wave nature, which plays an important role. They have a transverse cross section to the wave function, which is what you see here. And they can be, each mode is a way of transporting, and you get quantization of conduction when the transport is ballistic. When it flows without scattering, you get conductance that is in terms of the conductance quantum, E²/h, the fundamental constants, times the number of channels. And this was first discovered in semiconductor devices where you pinch off a two-dimensional system and only allow certain modes to flow. And in fact, so you can see the transverse modes by opening up that aperture. And in fact, really beautiful work that was done at Harvard basically showed that you could really visualize with microscopy and see these lobes. So here you see the first, second, and third lobes. This is from Bob Westervel's group. So the idea is that this is really the wave nature of electrons. And so it turns out that we see the wave nature of electrons in one-dimensional structures that we sketch with our atomic force microscope. So it kind of looks like this. And the idea is that this is a region where you have electronic subbands, and these are confined in the two transverse directions. And you can think of them as basically having an energy momentum dispersion relation that are separated by their energy structure. So depending on how many of these are filled, you will have a conduction of E²/h times the number of those modes. So on the top, there's only one subband occupied. And if you change the chemical potential, you can now occupy 3 of them. And you can climb this ladder by changing the gate that is on the side of this electron waveguide. And then these modes themselves, the bottoms of these bands, which we can measure, they can disperse in a magnetic field because there's also the spin degree of freedom and orbital effects and so forth. So the quantum mechanics of this basically is something that you could assign in a homework problem to an undergraduate. This is in 3 dimensions. It all pretty much separates out. You have the kinetic energy term, the confinement term, which you can model as a parabola or half parabola. And then you have the magnetic field, which couples to the spin, and the vector potential. So when you solve this, you get wave functions. These are like the the optical modes, but these are electron wave functions. The blue and red are the positive and negative signs of the wave function, and they're pressed up against the interface. And you can see that these numbers tell you how many nodes of the wave function there are in the horizontal and vertical direction. And then you can look at how they disperse in the magnetic field, and you get this pattern. that looks like this that shows you how these modes respond to magnetic fields. So the reason I'm showing you this is because we actually measure this experimentally. So we can model structures and fit parameters to get a pretty good agreement, which corresponds to the Landauer quantization of modes, of multiple modes through the system. So this is a very, very surprising result because actually these are not super clean materials in 2 dimensions. So they're nothing like gallium arsenide. So they scatter in less than 100 nanometers in 2 dimensions, but in 1 dimension, they can travel 20, 30 microns. So this is a really surprising state. I mean, we have systems where we have a single quantum channel of E squared over H and so forth, spin polarized modes. So this is a really, it's a building block, right, is what it is. So we don't exactly know how it fits in, but it's a building block, and it could be used to create quantum materials. It could be used maybe to sense quantum bits in other systems and so forth. So now I want to talk a little bit about this sort of non-perturbative quantum phases. I'll just spend a few slides on this. Again, it goes back to this. It turns out we spent a lot of time looking at this family of electron waveguides. And what we noticed is that if you just in Mathematica or whatever, you start to play around with the parameters, you notice that there are some magical values which correspond to the values of the confinement energies along the X and the Y direction. And it turns out that there's a special condition where you get this sort of increasing degeneracy or crossing of these modes. So you can really see that here in the diagram. So first you have the lowest mode, then you have 2 modes. Of course, they're always going to cross at some point if they ever cross. But then you have above that, you have 3 that start to cross at all the same point, and 4 and 5 and so forth. So when bands cross, that means that you have actually an opportunity for interactions. So interactions can really take place without sort of energetic costs. And so you can get, especially when you have strong electron-electron interactions. It turned out that we actually saw, so while I'm telling you the story in reverse, we would see this effect experimentally in device after device. And then we started to think about what's going on in the system. And the picture that we have right now, well, one of the striking things is that unlike these quantum point contacts where you have evenly stepped staircase, here the steps keep getting larger and larger. So it's going in units of E squared over H, you have 1, 3, 6, 10, 15, and so forth. So this is actually can be thought of as a diagonal in Pascal's triangle. So in honor of that, we call this Pascal condition, and the quantum phases associated with this are a Pascal liquid. So the idea is that if we were to sit at the Pascal magnetic field and change the chemical potential, we go from a phase where initially there was nothing because basically it's a vacuum, right? We call it the vacuum. But then you can change the chemical potential and get to a plateau of E squared over H. And now you have a single component Luttinger liquid, it's called, right? A single type of electron that can flow through this quantum wire. And then when you cross another point, now you've added another type of particle. And this particle actually is a bound pair of electrons, not superconducting, but it's also traveling on top. So it adds 2 to E squared over H because the charge is 2E. And then you can go further, and then you have now these trions, which are bound states of 3 electrons and so forth. So there's a whole family of emergent particles that come from the strong and as still unknown origin attractive interaction between electrons. Electrons should not attract each other, but they do in this material. And they lead to this exotic correlated electronic phases. Now, a trion phase is in the solid state actually is unique, right? I mean, of course, you have you have the nucleus, right? And so protons if you think about quarks, right, you have 3 quarks, so that's a bound state of 3 particles. But the point is that otherwise in nature, it's very hard to create a degenerate quantum liquid of these exotic phases. So the entanglement properties, for example, are completely unexplored and unexploited, but they could be really useful for future quantum technologies. Okay, so now I want to talk about something that maybe is more explicitly within the purview of this session on quantum simulation. Something that we've been thinking about and working towards for quite a while is the idea that we might actually, with the flexibility that we have with this platform, we might be able to create new forms of quantum matter, not just discover them like in that Pascal system, but actually create them, to engineer them. This is sort of like a long range vision, right, where you can simply put down a lattice of states for electrons to occupy. But we see this as a platform with the extreme nanoscale reconfigurability and the tunable properties and interactions as being a very promising approach. The challenge is, of course, we would like to create new forms of quantum matter, not just discover them. We would like to understand the sort of long-standing questions, let's say, even in this material. If we can understand why this material becomes a superconductor with so few electrons, we may be able to port that mechanism over to other materials and create really high temperature superconductors. We decided, though, strategically to focus on 1D systems. And there are sort of good reasons for doing that. The 2 main reasons are that 1D systems are actually tractable theoretically. So you can start to compare theory and experiment. There's a lot of techniques. Density matrix renormalization group is a principal one that we use. But also, as I will point out, this atomic force microscope is somewhat limited in its ability to create really large scale structures. But the idea is the same. You start with some base system and then you can perturb it, right? So that's generally, we have a platform, we're starting with some initial Hamiltonian, and then we're going to modify it in some way. We can create sort of different Hamiltonians from this starting point. And, I think of this as being, maybe along the lines of what Feynman had in mind. So we worked hard on this over a number of years. And I want to talk about, well, I already talked about this sort of unmodulated structure. This is just an electron waveguide, but I want to just briefly point out that we have, we have 2 recent papers where we performed different types of superlattice structures, one of which was involved a lateral degree of freedom. The other one was a vertical degree of freedom. So let me just focus on, okay, so the unmodulated one, I don't want to go over that again, but that's basically what I talked about. So that's sort of our H0, that's our initial blank canvas. So it's a 1D canvas, right, where everything is conducting. And then, of course, what you can do is you can remove parts of it in various ways or change it in the plane. And this is what we began to explore. So maybe it's easiest to talk about the lateral modulation because, again, what we're going to do is just not change the voltage of our tip, but we're just going to move the tip back and forth and create a superlattice. And so if we think of this in sort of in terms of perturbation, and we think about all those wave functions that we had to begin with, we're now admixing the lateral modes. And then, of course, we can ask the question, what's the impact of this? So it turns out always that this is, it's always more complicated when you actually do the experiments. And the reason is that these are not single particles, right? These are correlated electronic systems. And that's what leads to, some of the most interesting things. But what we were able to see were effects that do seem to be related to the engineering of spin orbit interactions in these quantum wire systems. And you can see that actually from this, from the electronic structure that comes from this image that you're seeing. The image is really showing where the electronic band minima are as a function of magnetic field. And the minima has shifted from being at 0 magnetic field to plus and minus 5 Tesla. So the idea of being able to just say, okay, I want this quantum wire to have a strong spin orbit interaction. This is something that in principle could be important ingredient for the design of, let's say, topological 1D quantum systems. In fact, we believe it may be the missing ingredient that you need for Majorana fermions in one dimension, getting Majorana zero modes, although we're not actively pursuing that right now. But it turns out that that what you see also are these tunable fractional plateaus. So these are also things that we believe are emergent states that come from the strong correlations between particles as they scatter these resonances. And there are a number of theory groups that are working to quantify this in more detail. So the second one is, well, maybe this is, I don't know which one is easier to understand, but this is an old problem, right? Vertical modulation. If you think, if you look back, I forget what year it was, 1920 something or so, Kronig and Penny, they wrote a model of a periodic potential, and the idea was sort of to describe what happens in a solid. The periodic potential in a solid, of course, coming from the periodic arrangements of ions. But we wanted to create an artificial 1D system. So what I didn't point out before is that superlattice modulation, the period of that modulation was 10 nanometers. Right, so this wiggle, one full wiggle is happening in 10 nanometers. Same thing is happening over here in our vertical modulation experiment. What we're doing is we're basically moving the tip to write a wire, but as we're moving it, we're modulating the voltage. So we can make it positive and negative or change the amplitude of the voltage. And that ends up creating a superlattice potential. And we work with a potential period of about 10 nanometers. And so what this ends up doing is you can actually see the sort of the backbone of a quantum wire, which has the modes that we have previously characterized, but now you see that they start to fracture, right? And the fracturing of these modes are due to this multiple scattering processes, and they lead to fractional states, basically all up and down the energy landscape of the system. So of course, we started out to create the textbook example of a 1D superlattice, but we end up seeing a much more rich physics that comes from the behavior of interacting electrons in a quasi one-dimensional environment. So now I want to talk, sort of bringing up sort of toward the present. We're sort of going from 1D to 2D. So we're ready. We're ready to go to 2D. We think that this is the right time, and we're armed with the right tools now. So for a long time, we've been using atomic force microscopy. It's been extremely powerful. We write lots of papers, but it's slow, right? So, and of course, we have lots of AFMs, right? We have a collection of atomic force microscopes, but the problem is that it's slow. And generally, they write at a speed of about 1 micron per second. That's sort of the typical speed, sometimes slower, sometimes a little bit faster. What I didn't tell you also is that this is like disappearing ink. So the structures are metastable. They decay in about an hour, roughly. And so that's kind of it provides a real constraint on the complexity of devices that you can create. So we also did learn that we can, if you put a single layer, if you want to work with other materials, like graphene, you can write through monolayer graphene, but you can't write through bilayer graphene. And forget about hexagonal boron nitride and all these other interesting 2D materials. So we were really limited also in that third dimension. But I had a wonderful student who tried, actually the third student who tried to do this. It's a very difficult experiment to demonstrate, but basically the idea was to use an electron beam that was tuned to really low voltages, 100 volts. And the hope was that those electrons would behave in the same way as the atomic force microscope. And so it turns out that it does work. And so this is an experiment sort of demonstrating how if you, instead of using an atomic force microscope, you just scan this low energy electron beam, you can see that this kind of jump when you, from one electrode to the other, of writing and erasing. The erasing was done with an AFM. But then you can also write through other layers, like, well, this one is graphene, but we know now that we can essentially write through any 2D material. You just have to adjust the voltage, maybe make it a little higher, but you can now write through stacks of materials, and you can subject those materials to whatever pattern of voltages you've created with your nanoelectronics. So we now have our own dedicated instrument and decked out. So rather than sort of once a month or once every few months access for a few hours on a highly subscribed shared instrument, we now have our own full-time system that has been customized and optimized for us. So this system is 10,000 times faster than an AFM, right? And it also operates in vacuum. So we have no problem with time constraints. And we can now really make extremely complex structures with the same precision as the AFM. So this spot size is 2 nanometers, right? The electron beam, and we've demonstrated this. And we can write through thick layers of hexagonal boron nitride and other stacks. We are super excited about the prospects of this. So we see, this is just one example of a stack of hexagonal boron nitride and graphene and making structures. This on the bottom right is, well, we didn't print that out yet, but this is the kind of thing. This is actually an array of nonlinear optical metamaterial device elements, but there are a whole range of things that one can do with this capability. And so, yeah, so this is kind of like the vision, the big scale where on all the way on the left, so of course we want to put this in the cloud, right? Why not, right? And so that you work with theorists who give you their ideas. You know, maybe it's in a Jupyter notebook or Mathematica, and they say, this is the thing, this is the quantum material I want you to print. And then we say, well, which substrate do you want to work with, right? Do you want to work with just the oxide, or do you want a magnetic layer? Do you want something else? And then they can select, and then we go print them out, and then we do measurements, right? So we've either created maybe some Fermi-Hubbard model, or we have instantiated some form of quantum spin liquids, or maybe topological phases, or maybe even have a way of making electron spin qubits. So this is, of course, a vision, right? This is not, we've not done this yet. We have some money though, which is great. We're super excited that we now have a DOE program that is supporting a group of 8 researchers, including Ben Hunt at CMU, who's actually the lead, because this is really focused on using these 2D materials and programming them. So this is something that we're very excited about. So again, taking a step back, right, perspective, 2021, correlated electronics, this burgeoning field. Well, I don't want to call it burgeoning, it's a tiny field that's growing. And again, from this diagram, like this material system, is it a new state of matter? Well, yes and yes. I gave 2 examples, 2 new states of matter. We have electron pairing without superconductivity, and then we have all of these 1D, sorry, we have the Pascal phases. And then quantum simulation, we have sort of two examples, two families of structures in one dimension that we've already demonstrated. And then all of the stuff about, well, can it be used, for quantum information? Can it be used to help process quantum information in other systems, or could it be used for quantum simulation in 2D? Or is it qubit? Maybe. So this is something that we're really excited to be working on in this year and in the years to come. So I want to acknowledge the collaborations, many collaborations, both at the University of Pittsburgh and outside. These are faculty, David Pecker, Roger Mong, who did some of the density matrix renormalization group modeling of the Pascal phases, and their students. Patrick Irvin is a research faculty who works very closely with me and my group. And then, oh, yes. So I work extremely closely with Professor Changbaum Ohm at the University of Wisconsin-Madison. He grows all of these oxide materials. This is theory group, Andrew Daly at University of Strathclyde, who also worked on some of these modeling of 1D systems. Graphene-based systems is work done with Philip Kim. Alex, I didn't talk about this work, but there's another project here that they were involved in. And I have many current students. This is actually just the sort of relatively recent group of students, both undergraduates and PhD students, who are the ones really responsible for this work being done. And then, of course, the support from a variety of funding agencies. So thank you for your attention.
Thank you, Jeremy. We have time for a brief question. Do we have one online, Steve? Are there any questions? Thank you very much. We are running a little bit behind, and so you can grab 5 minutes and grab something to eat, and we'll be right back.
Thank you.
Hold on a second. I haven't checked in the last hour.
I sent it this morning before I left. I'm over here. So you should,
No, I didn't get it. Can you send it right now?
Should I try to share my screen? Anybody there?
Yeah, we actually already have data, but we don't have it here. So we actually see like really understanding of the patterns. So yeah, we kind of like yeah, no, it was actually I suppressed it in the talk, but yeah.
I mean, I just want to say hello. Thanks for putting all this together. Yes.
Yeah, yeah.
We sort of met there. I think I should do sort of like grand niece.
question, although I didn't want to seem silly if it's something that's pretty easy. But so material sound could act like when an alteration could happen through got it. Or anything use that like that needle to hydrogen ions or just protons. And then when you're talking about some of the other different stuff and all those graphs and stuff, I lost me a little bit. But one thing I did that was based on the pattern printed on change. What exactly how the electrons mass matter? There was a horizontal.
Right, yeah. So it's kind of like, like in a row. So normally bumps are going down, but they're waves, so they conform to the. Yeah, I mean, I think that actually solids are arranged together. You can get electrons together and all that.
Okay.
So this is kind of a simple model.
Yeah,
One-dimensional lattice.
yeah, I think I got that now because I was thinking like
Oh, there it is. I think so.
Yeah, it doesn't. Yeah, it doesn't do anything with the hardware. It's just always your mind.
Okay.
Yeah, that doesn't do anything.
It's just that's also
Yeah, what's this?
yeah.
Another one?
Chris Savoy has one for that.
So
This is for Charles. He's doing it.
Yeah, well,
whose is this? Oh, that's okay. So which one do you actually need? Is it just the cubics one that you need from this one?
There's one by Kier. It's called URI presentation.pdf.
This one was. Oh, where we have that.
You already have that one. That's Kira.
What
This
about
one's
this conference one?
that was yesterday. Right?
Okay.
Yeah, that one's done. And this one's for Charles.
Next. No, he's Amir.
Yeah, Amir's on.
He's on. We're ready to go.
Yeah, let me just do this for you. So, these two?
That one.
Yes.
Well, we're ready to get started. Our next speaker is Amir Yacoby. He's professor of physics at Harvard University. He is also professor of applied physics at the School of Engineering and Applied Sciences at Harvard University and a visiting professor at the University of Waterloo. He currently holds the Lazaridis Chair in Physics. He received his PhD in 1994 from the Weizmann Institute of Science in Israel. His work focused on the understanding of coherence in quantum mesoscopic systems. During his postdoc at Bell Labs, Professor Yacoby developed new techniques to explore electrical conduction in quantum wires and was the first to observe spin charge separation in a hallmark of Luttinger's liquids. In 1998, Professor Yacoby joined the faculty of the Weizmann Institute, where he developed new techniques for imaging electrical charge in mesoscopic systems. Professor Yacoby joined Harvard faculty in 2006. His interests are in understanding the behavior of correlated electrons in low-dimensional systems and their applications to quantum information technology. In March 2014, his group developed a magnetic resonance imaging technology by which nanoscale images can be provided that could enable researchers to peer into atomic structure of individual molecules. In 2014, Yacoby was named a Fellow of the American Association for the Advancement of Science. Present to you, Professor Yacoby.
Thank you. Can people hear me? I just want to verify that sound is good.
Yes.
Okay, thank you. So first, I'd like to thank Vanita for inviting me, giving me this opportunity to tell you about some of the research we've been doing to develop new quantum probes for quantum materials. If I were to define myself as a physicist, I would say that I enjoy in particular working at the interface between instrumentation, the development of new measurement capabilities, and the discovery that comes with the ability to peer into matter with new approaches. And when the second quantum revolution emerged, it was pretty clear that having quantum mechanical systems that are extremely highly controllable and very sensitive to environmental perturbations would really revolutionize our ability to perform measurements. And so what I'd like to talk about today is one particular development that we have been pushing within our group, and that is the use of nitrogen vacancy centers as quantum sensors for quantum materials. Now, you might ask yourself, why do we really need more measurement techniques? After all, our measurement toolbox is extremely rich. And the question is, are there any challenges that our current measurement toolbox cannot address? And so I'd like to spend the first few minutes just motivating the need for new measurement approaches. And in particular, I'd like to describe some of the developments in recent condensed matter physics that really warrants more thought about how can we probe these systems. So on this slide, I'm showing a few examples of, and by no means this introduction is going to be comprehensive, it's just going to show a few examples of the things that potentially are very interesting to learn about materials that we currently do not have real easy access into. So this slide is about ground state properties of materials. And up here on the right, I'm showing a quantum spin Hall insulator. This is a topological insulator living in 2 dimensions. The middle section here is a quantum well. And we know that in a topological insulator, the underlying bulk states are gapped. However, there are conduction states at the boundaries, and they carry electrical current. There is two counterpropagating edge states, one carrying spin up electrons, the other going in the other direction, carrying spin down electrons. And when you look at this enough, you appreciate the fact that there is no net current, charge current flowing at the end, but in fact, there is a net spin current. And currently, there aren't really any probes that allow us to measure spin currents. How would we detect the existence, the presence of this steady state thermodynamic flow of spin at the boundaries of topological insulators? Another example is here at the bottom left, where the pink here is a suspended graphene sheet that we've studied a number of years ago with suspended top plates to explore very high quality monolayer and bilayer graphene. And what was realized in these systems is that when you subject graphene, the electrons in graphene, to a strong magnetic field out of the plane, when the density in this system is tuned to the Dirac point, namely to zero density, actually the system developed into an antiferromagnetic state, shown here in the inset, where the spins are actually pointing largely in the plane. They're canted a little bit out of the plane because of the external magnetic field, but nonetheless, they prefer pointing into the plane. One points in the sublattice A pointing in one direction, sublattice B pointing in the other direction. And you might ask, well, we do have techniques that allow us to measure antiferromagnetism and ferromagnetism in general. These are, for example, neutron scattering techniques. However, the challenge with this material is that, number one, it's a monolayer, so the volume of the material is extremely small. Number two, the density of electrons is exceedingly small. It's about 1 million times smaller than what you'd find in a conventional ferromagnet or antiferromagnet. So the sensitivity that's needed in order to know that indeed an antiferromagnetic ordered state exists in this system doesn't currently exist in an existing apparatus. Now, you might say, well, what about excitation? So suppose I look beyond the ground state of a material and ask, well, what type of excitations can live in some materials? And here again, over the past decade or so, there's been tremendous developments in appreciating the fact that there are many, many novel types of excitations. And the question is, do we have the tools to study them? So one example that was already mentioned by Travis this morning is quantum spin liquids. These are highly entangled states where the underlying system doesn't order magnetically. It forms a superposition of all possible singlet pairs between any two electrons. But the excitations above this peculiar ground state ends up being a collection of what's called spin-ons. Turns out that these are fermions, namely they have Fermi statistics. They do not carry charge and they carry a spin. And here again, you ask, well, how would I detect the presence of these spin excitations? How can I study their existence, the spectrum of these excitations, their dispersion? Another example that was mentioned also earlier this morning are non-abelian topological superconductors, where there the elementary excitations are non-abelian particles. And here again, our toolbox for exploring the presence of these non-abelian scatterings is extremely limited. Now, in a system that has excitations, and if these excitations are long-lived, one can then further ask the question, well, what about their transport? Can I define a chemical potential for these excitations? Can I look at gradients of chemical potential that will then generate currents? How would I study the current associated with these gradients in chemical potential, and so on and so forth? And here again, just representative two examples. One on the top right is the idea that in a magnetic system where the spin excitations are actually bosonic, unlike spin liquids where they're fermionic, spin excitations can condense to form a superfluid. And then one could ask, well, what would be the result of gradients in phase of the order parameter of this superfluid order, and that leads to a superfluid spin current. So how would we probe the generation of superfluid spin currents in magnetic insulators? Another example has to do with, again, spin liquids and the fact that quasi-particles in these systems can carry heat. And it turns out that in these systems, heat transport is by these Majoranas, by these non-abelian excitations, is expected to be quantized, and there are ongoing experiments trying to observe this. But again, our ability to measure heat transport and temperature gradients on the mesoscale is rather limited at the moment. So I think the punchline that I'm trying to convey is that whereas we have tremendous capabilities in measuring electrical properties or optical properties, for the examples that I showed today, namely mainly spin characteristics, and other quantities that I'll talk about today, we're really lacking in experimental techniques, and we really need to push forward the development of new capabilities, and with them will come new discoveries and deeper understanding of what's happening in these materials. So what I'll talk about today is a subset of the activity that's ongoing in the group, and that is the use of nitrogen vacancy center as magnetometers. And what you'll see is that they do allow us to access the ground state properties of materials on the nanometer scale. It allows us to probe mesoscopic systems. So it's not going to replace the things that we can do on bulk systems with X-ray diffraction or neutron scattering, but nonetheless, they will allow us new insights into systems where mesoscale is key, for example, hybrid systems. And it does allow us to explore underlying excitations. I'll give a few examples of that. And finally, transport both of electrical currents and other types of currents like spin currents. So over the years, we've been developing this technique, which essentially can be summed up as the ability to measure magnetic fields as a function of time, or in Fourier space as a function of magnetic field, the spectrum of magnetic field fluctuations. So this is what this technique allows us. But if you understand the physics of how these magnetic fields or their fluctuations can connect to different physical phenomena, it really allows you access to a variety of other physical quantities. And here I just give a few examples of things that have interested us over the past several years. On the top right, we have the ability to measure using this technique the density of paramagnetic spins. This is essentially what an MRI does. And what we were able to show is we can do three-dimensional reconstruction of spin density, but on a nanometer scale rather than on a millimeter scale, which is what you find in commercial MRIs. Another quantity that one could look at, which is a ground state property, are spin textures in novel magnetic materials. Here, for example, is an image of the magnetization of a skyrmion in a thin material. And here again, this type of material, cobalt, iron, boron, is not a very nice and ordered material that allows you to do Lorentz microscopy to see the skyrmions, and actually doing the microscopic imaging with this magnetic sensor that I'll talk more about was key. You might say, well, the connection between magnetization and magnetic field is not that surprising. We know it from Maxwell's equations. However, it turns out that there are infinite set of magnetization that produce precisely the same magnetic field outside of the material. And so figuring out techniques of how to actually pin down the actual magnetization while measuring magnetic field was the real challenge in this example. I'll talk about today, in this third example, our ability to measure spin chemical potentials. This is the chemical potential of spin excitation in a magnetic insulator, where the spin excitations are bosons and not fermions at the moment. I'll talk a bit about the ability to image electrical current in mesoscopic conductors. And you might say, well, what should be surprising there? Well, as you'll see, it turns out that the interaction between electrons, which is often what delivers a very interesting and counterintuitive behavior, is also at play in these systems. And you get phenomena that resemble what happens when fluid or air flows above an airfoil or flows through a pipe. And the last example that I'll focus on is in the bottom corner here. And this is the use of NV centers to image spin waves in magnetic insulators and to use these spin waves as a new way of imaging materials. So I'm sure you've all heard some talks about NV centers, so I'll be rather brief about the underlying properties of nitrogen vacancy centers. These are defects in diamond. They consist of a nitrogen substitution atom and a missing carbon atom, a vacancy. This bond here forms an axis along which we're measuring the magnetic field. The spectrum of this complex defect is actually rather simple. It's a spectrum of a triplet that has a zero field splitting shown here. The ground state is an MS equals 0 state, and we have two excited states that carry MS plus and minus 1, and they disperse in a magnetic field according to a G factor of 2. So we know precisely at each magnetic field what the energy of this defect is. And so the way to probe a magnetic field in this system would be to scan a microwave signal at different frequencies. And once the microwave system signal is resonant with the energy levels, we will see absorption in this defect that will tell us precisely what the magnetic field is. A key feature of this defect is that we can measure eventually what the underlying state of the system is, whether it's in its ground state or one of the excited states, simply by fluorescence. When you shine light on it, it emits red light, and the intensity of the red light is stronger if the defect is in its ground state as opposed to its excited state. Another very nice advantage of this system is that it is operational at any temperature. Diamond is rather, doesn't change much as we change the temperature from millikelvin temperatures to above room temperature. And ultimately, the sensitivity, at least for the applications that I'll be talking about today, the spatial resolution of this technique will be determined by the distance between the defect to the material of interest. So that will motivate us to bring this defect as close as possible to the object under study in order to gain spatial resolution. So what makes this defect a quantum sensor? Well, what makes it a quantum sensor is the fact that we know how to initialize it into one of its two states, let's say the 0 state. We know how to control it precisely, generate any superposition we desire on the block sphere described here. And the reason I'm focusing on 2 levels only is because at any finite magnetic field, even though it's a 3-level system, we can focus on a subset of 2 out of the 3 states. So we can control it arbitrarily, and we can detect its spin state at the end through this fluorescence and know whether the defect ended up in its ground state or excited state. So what's the connection between this 2-level system and magnetic field sensitivity? So imagine we initialize this state in the North Pole on the 0 state. We then control it to project, to rotate this spin into the equator, which forms this quantum mechanical superposition of 0 plus 1. And now in the presence of an external magnetic field, this spin will precess and acquire a phase. And the time that we can process is simply given by the coherence of this defect. So if we have an unknown field omega, the phase that will accumulate is going to be omega times the coherence time T2. This is our signal. In order to assess the sensitivity, we need to understand what the noise is. And of course, this is a quantum noise. This is a quantum system. So when we measure, we're going to be projecting this defect onto either the ground state or the excited state, which means that our uncertainty in a single measurement is of order pi. But we can improve on that by repeated measurements, and we will then improve our noise by 1 over square root of the number of measurements. And so easy math to show that the signal has to be greater than the noise, and that gives us a sensitivity that we can detect omega fields that are largely given by 1 over the coherence time and get improved as we improve the number of measurements. And if we translate this by using some typical numbers for the coherence of an NV center of order 100 microseconds, and we repeat this measurement so that we have an integration time of 1 second, this translates to about 10 nanotesla per 1 second of integration, or per root hertz for those who are familiar with the units of sensitivity. So to give you a sense whether this is good or bad, let me just mention that if I had a single electron that has 1 Bohr magneton, electron dipole moment, and you're asking what is the magnetic field of this system 10 nanometers away from the electron, that magnetic field is an order of 1 microtesla, so 100 times greater than this sensitivity. For a nuclear spin, we're a little bit too noisy at the moment. Of course, the signal at 10 nanometers is on the order of 1 nanotesla. And so one needs to integrate quite a bit in order to be able to detect single nuclear spins. And there has been tremendous development on doing that in the community as well. Now, one of the remarkable things about these NV centers is that they not only allow you to measure a static magnetic field, which is what this protocol describes, but by utilizing more complex pulse sequences, like echo techniques or multiple pulses, we can actually isolate from a magnetic field spectrum any portion of the spectrum that we desired within a bandwidth that spans DC to several gigahertz of magnetic field fluctuations. And it's really a matter of figuring out what the pulse sequence that we want to apply to the NV center in order to shape a filter function that would then extract a particular section of this spectrum of magnetic field fluctuations. So this is really the power of the technique. And as I mentioned, it's basically a magnetic field sensor that allows us to measure magnetic fields either as a function of time or as a function of frequency in a bandwidth of DC to several gigahertz. Now, in order to turn this into a scan probe, in 2012, we started developing these diamond cantilevers, where we start out from a monolithic sheet of diamond, typically 50 micrometers thick, and we then pattern on it pillars, and then from the other side, we thin it down to a very thin slab. And so this entire platform here is one chunk of diamond. We're not attaching the tip, we're fabricating the tip out of the monolithic piece of diamond, and the intensity of light is guided through the pillar. So the role of the pillar here is twofold. One is to have a single defect sitting really at the apex, 10 nanometers away from the surface. And the other is to guide the light out. The amount of light that we can collect from this defect will eventually determine the signal to noise and the performance of this tip. Whereas these were the original generation of our cantilevers, currently we're working with much bulkier cantilevers shown here on the right, so we don't thin it down anymore. We do have the pillars at the end shown here. This is a 2 to 3 micron pillar. We have full control over the taper. That helps a lot in extracting light out of the pillar. And again, there is a single NV center defect sitting roughly 10 nanometers away from the surface. And we're starting to integrate the microwave signals also, such that these pillars are now sitting on commercial AFM cantilevers with the microwave signal attached directly to the cantilever so that they're compatible with other AFM technologies. So I'd like to start by giving you several examples today of the various capabilities that this technique enables and what kind of new physics can it give us access to. So I already mentioned the notion of spin superfluidity. And if you think about a magnet as a system that has spin waves, these are just the motion of correlated spins due to the nearest neighbor exchange interaction between the spins and their long-range dipolar interaction. It turns out that these spin waves in conventional magnetic systems, both ferromagnets and antiferromagnets, can condense to form a superfluid. And you can then ask, well, what would be the supercurrent associated with this superfluid? And this is basically the long-distance transport of angular momentum. Now, you might think, well, this sounds like a very modern topic, but in fact, the origin or the beginning of this idea of spin superfluidity is more than 50 years old now. And this is started with the seminal paper by Halperin and Pierre Hohenberg, titled Hydrodynamic Theory of Spin Waves, where they outline in the abstract, the first sentence is the key statement. A hydrodynamic theory of spin waves is developed for certain magnetic systems in analogy with the derivation of two-fluid hydrodynamics for liquid helium. So what they appreciated already then is the fact that a magnet can be described one-to-one, just like superfluid helium, with two types of fluids. One is the superfluid density and the other is quasi-particle excitations. So just to give you a short background on what these spin waves are, so if I have a system of spins and they're coupled through exchange interaction locally, then the rotation of these spins is going to be, and their excitation, each one of these spin waves here carries one unit of angular momentum h bar and has both momentum and energy. And the dispersion in an exchange type of system is just parabolic. And interestingly, this spectrum has an energy gap below which there are no spin excitations whatsoever. And what generates this exchange gap is an anisotropy in the system. And this anisotropy could either come from intrinsic crystalline anisotropy, or, for example, from an external magnetic field that favors the orientation of all spins to be along the magnetic field, and therefore penalizes any spin that wants to fluctuate away from the direction of magnetic field. And what this blue line marks is how the magnitude of this spin gap depends on an external magnetic field, this anisotropy. This is known as the Kittel law and has this very characteristic square root dependence on magnetic field. Now, if this bosonic excitations condense, well, what are the salient features of a condensed Bose-Einstein condensate? Well, we know that upon condensation, the system develops a macroscopic order parameter where the amplitude of the order parameter captures the density of excitations in the ground state. And what we know, or what we learn already very early on in our physics studies, is that in a Bose system, as we increase the number of excitations, the chemical potential can increase, but once it hits a state or a collection of states, then it gets pinned, because at that point, macroscopic occupation of the ground state occurs and the chemical potential will rise no more. Unlike a fermionic system, where as we increase the density in the system, the chemical potential will rise indefinitely, for a Bose system, we have pinning of the chemical potential precisely at the bottom of the spectrum of possible excitations. So for our spin wave system, this would be precisely the bottom or the top of the spin gap. Now, you might ask, well, what is the connection of these spin waves and condensation to a magnetic sensor? Well, the key is to understand that once we have a chemical potential in the system, we have magnons, we have these spin waves in the system. They're producing fluctuating magnetic fields because each one of these spin waves is generating magnetic fields into space. And it's the noise associated with these spin waves that we can detect. So if this is the spectrum of our NV center at just some magnetic field, it turns out that noise precisely at any one of these frequencies, the difference between the energy levels here, is going to generate relaxation of the NV center. So regardless in what state we started, after some time, our state is going to decay into one of the other states, and the rate of decay tells us about the magnitude of fluctuations in the system. And it's a quantitative thing. So it turns out that you can extract precisely what the chemical potential of this Bose system is by doing two measurements. One is the rate of relaxation of the system in the absence of any excitations beyond what there exists due to thermal fluctuations. And the other is a rate of decay when we have more, when we increase the number of spin waves in the system. And this is the result of this chemical potential as a function of the number of excitations on the right and magnetic field on the left. And what you can note is that for any value of magnetic field, the chemical potential rises initially, but then gets pinned, and it gets pinned precisely at the bottom of the dispersion or the top of the spin gap in the system as defined by the Kittel law. So this was a very, very nice and exciting example that we can actually measure spin chemical potentials. And now we're interested, for example, in looking at gradients in chemical potential of the spin system, which then is driving a spin current, and to relate measurements of spin current to gradients in spin chemical potential to extract spin conductivity and other quantities that can characterize the material in ways that have not been possible before. The second example that I'd like to present today is one that addresses a different type of flow, and this time it's electrical current. And you may ask, well, what's special about electrical current flowing in a mesoscopic conductor? Well, number one, we heard already from Jeremy, we can have ballistic conduction. But the topic that I'll talk about today is actually not ballistic conduction, but a situation where indeed the mean free path of the electrons and their scattering due to imperfections or other impurities or phonons is very small, but they interact strongly with one another. So when we study electrical conduction, we're familiar with the Drude model where the electrons scatter off of impurities or phonons. Basically, they relax their momentum very frequently, much more frequently than they scatter off one another. And that's why we can think of them as independent electrons. And basically, we have a saturation velocity that's proportional to the electric field applied to the system, which defines our mobility. But imagine a system that's extremely, extremely clean. Means that the particles, the electrons in this system, are traveling really long distances without hitting any impurity or scattering off a phonon. They might scatter off the boundaries, and I'll talk more about that. But what they're doing very frequently is they're scattering off one another. And so their electron-electron scattering time is much shorter than the momentum relaxing scattering time. And these are the conditions under which the collection of electrons conserve both energy and momentum. If you think about it, each electron here doesn't conserve its energy or its momentum. It transfers it or gains momentum and energy from the other electron system. But the sum of all of these is conserved, and that's the underlying reason for hydrodynamics in this system. So the question is, under what conditions will the manifestation of hydrodynamic physics be seen, and what can we observe? So number one, if we want to maximize this inequality, namely maximally shorten the electron-electron scattering time relative to the momentum relaxing time, it turns out that going to a system that has very low carrier density does that. Because the electron-electron scattering time depends as 1 over the Fermi energy, and so, the scattering rate depends as 1 over the Fermi energy, and therefore having a low carrier density in the system will generate rapid interaction between the electrons. And if the system can nonetheless maintain its mobility, then we're in business. So already several years ago, on the order of 5 years ago, there was some interesting indications from the group of Andre Geim in using graphene that indeed the system develops this viscosity that has to do with the interaction between electrons while the overall momentum and energy is conserved. And they were able to extract what the viscosity parameters in the system are all the way up to nearly room temperature. What we were interested in is to see the analogies between this hydrodynamic fluid and fluid mechanics, namely the Navier-Stokes equations, and the fact that when you take a fluid and you flow it through a pipe, because of the interaction of the fluid with the boundaries of the pipe, the velocity of the fluid tends to go to 0 at the boundary and maximize it in the middle. And you can ask, well, is this really what the electrons will do inside a conductor? So if you solve these Navier-Stokes equations for 2 types of conductors, one, which is more the Drude-like, namely a lot of momentum relaxation present in the system, you end up with a current profile across the channel that's uniform. And that's what we expect. We expect current in our copper wires to flow uniformly across the wire. But if you now improve the mobility in your system, it turns out that you expect this parabolic profile where the current density is postulated to go down to 0 at the boundary. So now several questions exist. Number one, suppose the electron system is indeed very hydrodynamic. Will the velocity go down to 0 at the boundaries? And 2, if it does, what is the current profile that emanates? Is it indeed this parabolic profile? So NV centers became extremely handy in underlying and exploring this phenomena, simply because when you have electrical current, the motion of charges generates current, it generates magnetic fields that we can pick up. And here again, there is a very simple relationship between the quantity that we know how to measure, the magnetic fields, Bx and By in the system, and the current density in the system. And I'm not going to go into detail about the specifics, just to note that there is a known piece of physics that connects what our sensor knows how to measure and the quantity of interest. And so what you see in the bottom here is a quiver plot, basically a plot that shows the direction of current. The boundaries here, which are these dark red lines, mark the boundaries of the graphene sheet that we patterned. So we have a wide channel here, about 1 micron wide, and the current is sent downwards, then to the left and out through the bottom left contact. And what you can see is that the intensity of the current, which is the color, is indeed peaked in the middle. And you can see that the current density when the channel is narrow is higher versus the current density when the channel is wider. And this all makes sense. But now we can really look carefully with our scanning NV and map out and extract what the current density is as a function of position. And these are these red data points. And what you can note is, first of all, an experimental observation. And that is that the current density at the boundary is going to 0. This is not an assumption. This is an observation. Second, you can see that the current indeed peaks in the middle of the sample and follows very much closely to what we expect. And this is this parabolic profile. And I want to emphasize that this behavior that you're seeing here all happens at room temperature and at the charge neutrality point, where the density of electrons is essentially 0, and you just have a plasma of both electrons and holes because the system is at finite temperature. Some of our test results, some of our calibration results were to use low mobility graphene, which are the yellow dots. And indeed, you see that over the same length scale, you get a very, very flat profile. And you can also take a thin palladium wire, which again is very disordered, and you get the gray dots, which again is very flat. So indeed, electrons behave hydrodynamically. And we are now attempting, obviously, to see whirlpools and all the hydrodynamic manifestation that a system of interacting electrons can manifest itself. Interestingly, the motivation to look in graphene was the fact that carrier density is very low, and that's where hydrodynamic phenomena should be maximized. But we asked ourselves, can there be a system in which the carrier density in the system is actually very high, and yet it still exhibits hydrodynamics? And a candidate material that we decided to look at is tungsten telluride. Tungsten telluride has a fairly large Fermi surface. It is also a semi-metal. It has both electrons and holes in equilibrium. It's exfoliatable, so we can use thin films of this material. But it has both large hole pockets and electron pockets, which means that the underlying electron-electron interactions should be fairly weak. And in fact, if you do look at the mean free paths associated with various mechanisms, you see that indeed the mean free path for electron-electron interaction is very long compared to the impurity scattering length. So there's no chance that this system will be hydrodynamic in the conventional sense. But when we started doing these measurements, we actually did see hydrodynamic behavior. And what we immediately realized is that there is a new mechanism for electron-electron interaction in this system. And this is one electron coherently emitting a phonon and another electron far away absorbing precisely that same electron. So this is a phonon-mediated electron-electron interaction. And what this means is that now over long distances, these electrons can interact in a way that still collectively conserves energy and momentum and would lead to hydrodynamic behavior. And so when we looked at these current profiles, we indeed saw very non-flat current profiles, and they had a very interesting non-monotonic temperature dependence. So these are the current profiles in this kind of topographic viewpoint as a function of temperature as you go from 90 Kelvin down to 5 Kelvin. And you see that it becomes maximally hydrodynamics somewhere around 10 to 20 Kelvin. And it turns out that this agreed very, very well with theoretical first principles calculations that use this phonon-mediated electron-electron interaction to describe the origin of hydrodynamics in the system. The last topic that I'd like to talk about in the remaining 10 or so minutes, or 8 minutes, is the use of NV centers as a means to develop an entirely new scattering platform. So I'd like to start by introducing generally what a scattering platform is. You're all familiar with it, but just I want to highlight some of the amazing benefits that we know scattering platforms have in providing information about and characterizing materials. So the idea behind a scattering platform is that we have some coherent source of waves or particles. These are traveling, let's say, in vacuum here, so in a medium where we understand their behavior very, very well. There's no unknowns associated with the propagation of these waves in vacuum. But then these waves impinge some target and get diffracted. Now, often we try to measure the properties of the materials in the material. But the nice thing about a scattering experiment is that we're actually looking in the far field. We're going to collect the scattered particles or waves far away. And by measuring the intensity and, if possible, the phase in relation to the incoming phase, we can reconstruct the underlying scattering function that caused this scattering to occur. And this is the basis of X-ray scattering that allows us to reconstruct the structure of material. This is the basis of neutron scattering that allows us to reconstruct underlying magnetic order, et cetera, et cetera. It's an extremely powerful technique. And again, I emphasize the fact that we don't need to measure the properties of these waves where the interaction happens. We can measure it far away and using inverse Fourier techniques, reconstruct the underlying scattering experiment. So the question that we were asking ourselves, well, what about magnons, these spin waves that I talked about before? Can we use them as the particles that are used to scatter and diffract off of an interesting medium? And Travis already showed this image in his talk. This is kind of our artist rendition of what we're trying to do. So the gray slab here is a magnetic insulator, and it will serve as our vacuum. This is the material in which the spin waves that we will generate behave in a very known and predictable way. The way we excite them is using an antenna, this yellow strip here that sits on the surface of this magnetic thin film. Oscillating currents generate oscillating magnetic fields, and these drive spin waves parallel with wave fronts parallel to this antenna. These spin waves then propagate, and their frequency is set by the frequency of the alternating current in the antenna. Their wavelength is simply set by the dispersion of our medium, which is what I call our vacuum medium. This is our slab. So there's a well-defined dispersion relation between momentum and frequency. Once we define the frequency, that sets a wavelength. Now, these propagating waves in YIG, for example, which is the vacuum material that we're using, they can propagate for millimeters with barely any dissipation. These are very low loss dissipation materials. And now imagine on top of this material, on top of our vacuum, we place an unknown medium, a medium in which we want to understand the interaction of this medium with spin waves, or the structure factor associated with scattering of spin waves. This material then will diffract our spin waves. And if we had a way to measure the amplitude and phase of these spin waves far away, we can then reconstruct the underlying properties of our scatterer or the target material. So the ingredients is that we need to be able to launch coherent waves with well-defined energy and momentum. This is something that has already been shown previously in YIG. We need to be able to detect the scattered waves, ideally both the amplitude and phase. And this I'll show that NV centers are extremely powerful in detecting both the amplitude of these traveling waves, these are not standing waves, they're propagating waves, and the relative phase in relation to our input into the incoming wavefronts. Of course, we want to make sure that our spin waves that live in our vacuum have an appreciable interaction with the material. And lastly, we need to be able to reconstruct from our scattered information what the underlying properties of the material is. And as you'll see, this is one of the harder parts here. I believe this is the hardest part in any scattering experiment, is the inverse problem. So let's focus on imaging first. How can we image these traveling waves? So just emanating from these antennae, as I'm plotting here, we have these spin waves that are characterized by a fluctuating magnetization that thereby produces a fluctuating magnetic field that has a frequency-dependent I omega t and a momentum-dependent IKX. And K and omega are related through the underlying dispersion of the medium, which is very well known. Now, what you should note is that this magnetic field is time varying. And if that magnetic field precisely meets or agrees with the energy separation of the two levels of our NV center, it will cause transitions. And in fact, it will cause coherent transition, Rabi oscillations. More interestingly is the fact that this oscillating magnetic field has a phase which is position dependent. So at one position, this phase is 0, the other one it's pi over 2, and then pi, etc. And it turns out that the phase on the block sphere determines along what axis will this spin oscillate from the 0 to the -1 state. So the time varying component drives coherent oscillation from 0 to -1, but the phase decides what axis is it rotating around in the plane. Now, if we were only to measure the intensity, then we can just project the NV center later on and just see, are you 0 or 1, and we'll know whether we've precessed and how many precessions have undergone due to this time-varying magnetic field. But we want to know also the phase. And so in order to do that, we supply the NV center with a position-independent reference signal, which is shown here in purple. And the total magnetic field that the NV sees is therefore the reference signal plus the one due to the spin waves. And you see that there will be positions in which the spin wave axis is exactly opposite to the reference axis, which means that we will have no oscillations. And there are others in which they sum up coherently and we get very fast oscillations. So this is the mechanism by which we can image these spin waves in space. And again, I emphasize these are propagating waves. So if you look here, what you're seeing is now exactly these propagating waves. Their wavelength in this particular example are a few microns, and we are now able to go down to several hundred nanometers. And current experiments are pushing down to several tens of nanometer of spin wave imaging capabilities using the NV centers. Now, once we have this, we can now focus on what happens if we had a target. And this target is a permalloy. It's basically another piece of magnet that we put on top. And we're looking at how these spin waves scatter off of this target. And what you see here in the bottom right is the measured intensity of the spin waves in space. You see there's a lot of complicated physics going on near the target, shown here in this white circle. But far away, we get a scattering pattern of the intensity. And we can now measure the phase also. And you see, again, complicated evolution near the scatter, but something that becomes a little bit more organized in the far field. And now we can use these two far field pieces of information, the amplitude and phase, or the real part and imaginary part, in order to reconstruct the underlying properties of the target. And I'm going to be very brief here because this is really a challenging process, but I just want to give you a sense of what is the underlying properties of the target that are generating these kind of images. So if you think about the target is magnetized here, and it has a magnetization M0. It's interacting with the fluctuating magnetization of the spin waves. So we're looking at the fluctuating component of our target. at the frequency of the spin wave. Because this target is fully magnetized in the X direction, fluctuations can only occur in the Y direction. So the magnetization is fluctuating in the Y direction. And without going too much into detail, it's simply a result of Maxwell's equation. In fact, what we're really sensitive to, the magnetic field, is sensitive to the divergence of the fluctuations of magnetic field. And you see that there is only derivatives of these magnetizations at the boundary. And it's positive on the top side and negative on the bottom side. So in fact, our source looks like a dipole. And indeed, if we compute the scattering signal from a dipole, shown here, the left is our experiment, the middle is a simple dipole, we see that we're getting already pretty close in terms of the phase information and somewhat close in terms of the amplitude information. But now we need to iterate. We can add a smaller quadrupole component and then the next moment, etc. And you see that we can converge slowly to understanding precisely what the underlying target is in this kind of moment expansion technique. So I'm running out of time, so I'd like to just summarize and primarily maybe say, especially to the graduate and undergraduate students in the audience, that developing new measurement capabilities is really extremely important in exploring materials. And it's part of this cycle of discovery where new techniques allow you to discover new material properties. And sometimes these properties and this new chapters of physics that you unravel will provide new ways of looking at material and the development of new techniques, and the cycle continues on and on. And with this, I'd like to pause here and thank you for your attention and take some questions if there's time.
Thank you. That was very nice. We have a question over here.
Thank you so much for Amir for that amazing talk. So I had a question. Are you thinking about maybe using magnons or spin waves as for distributed sensing as well? Is that an avenue that might be possible?
Right. So I think, the idea of magnons is basically to use their coherence, their well-defined energy and momentum in order to basically do this scattering experiments on complicated matter. And obviously, this is not going to replace neutron scattering on bulk systems, but as you can see on mesoscopic systems where the size, for example, layered materials or twisted magnets or even superconductors, clearly there's going to be a scattering signal because the time varying component of the magnetic field will induce currents in the superconductor and scatter the spin waves. So you can ask, well, why should I indeed need to use a scanning NV? Can I do parallel imaging of the scattering waves, maybe with an array of NV sensors or with a high density of NV sensors? And these are all great ideas. We are interested in doing that. We're pursuing this with ensembles of NVs. Obviously, then you're limited in the spatial resolution. But the nice thing about the far field is that features become separated the further away you are. So you don't necessarily need the nanometer scale. But if we want to go down to wavelengths that are on the order of 10 nanometers or so, or tens of nanometers, so that we can really look at underlying order in Moiré systems, for example, then we still will need this high spatial resolution. But yes, I think the idea of looking at parallel imaging of these spin waves using NV sensors is going to be an extremely important development.
Yes, we have an online question too from one of the attendees. Michael Perrone asked, how would you in general separate the interaction of the spin waves with the junction between the YIG and the sample and the spin waves with the sample itself? Is it possible to imagine for a different vacuum material, you would get different spin wave diffraction due to special properties which arise as the material interface, which do not arise for the sample material in free space? For example, with the superconducting or topological insulator sample?
Yes, this is an excellent question. And so I want to stress that I think part of the power of this technique is actually looking precisely at that interface. or at interfaces in general, right? I mean, generally techniques are very, accessing interfaces is very inaccessible. So indeed, there is complications, right? The interaction, I can imagine the interaction between the spin waves in our vacuum system, in our YIG, and the material of interest here as being either through the exchange interaction or through dipolar interaction. And in fact, if you want to think about what the target really is, it's incorrect to think of the target just as this white circle, the material that we deposited. In fact, this material perturbs our vacuum to form a hybrid system that is of interest. And what the scattering is telling us is precisely about this hybrid interaction of our material and the YIG. Now, if you wanted to isolate and separate the contribution of exchange interaction from the dipolar interaction, then you could perhaps, for example, put an insulating layer, very thin insulating layer between them, such that you'll suppress the exchange interaction, be left only with the dipolar interaction. Additionally, if you want to separate the role of the conduction properties of the materials, then you might be able to tune the material from an insulating state to a conducting state and see what the induced EMF is doing. So what I want to state is that the interaction is complex. And this is, I think, part of the interest in this system, is that it really provides us insight into this hybrid system or hybrid systems, where one could really look at the interface between materials and not only at the kind of underlying bulk property as if it were in vacuum. But one needs to take all these things into consideration.
Thank you. We have another question from Jay Wang. It's a short question. I may have missed it, but what is the order of magnitude of the Rabi frequency and what parameters affect it?
So it turns out that you can drive Rabi oscillations with these spin waves that are extremely powerful, very rapid. So the intensity of these spin waves can get fairly large. Number-wise, you can get Rabi oscillations that are in the range of tens of megahertz to 100 megahertz. Typically, we don't want such strong Rabi oscillations, and because this would mean that our incoming spin waves are very strong. And the way I describe the scattering of these spin waves off of our target is in the Born approximation, where you have most of the spin waves going across and you have some weak intensity that's scattering. Of course, nonlinear effects will be extremely important if the intensity of the incoming waves are large. And this would be very interesting because it would allow us to look at the nonlinear structure factor. Obviously, there is a lot of interest in looking at inelastic scattering. So what I described was elastic. The incoming waves have the same energy as the outgoing waves, but they're going to be inelastic processes. So can we detect those with these techniques? These are all things that we're working on theoretically currently, as well as trying to implement experimentally.
Thank you very much. Let's thank Amir again.
How's everybody doing? All right, so this is the second session on quantum information science education. And I'm delighted to introduce our first speaker, who's Bob Joynt. Where is Bob? Oh, there he is. Okay, he is a professor of physics at University of Wisconsin-Madison, where he has served as the department chair and also the associate director of the Materials Research, Science, and Engineering Center. Research in quantum computing spans a variety of fields. Also the founder and director of the NASA's program in quantum computing, which is the first such program in the entire country. And today he's going to tell us about
Oh, okay. Hook up this one.